So you're factoring each of these that can be factored. Just to start off with, let's take a look at the first one here, x squared minus 25. When you see x squared minus 25, you are multiplying a negative 25 and you're adding to 0. And the reason is because really that's the same as x squared plus 0x minus 25. 0x though, we don't have to write it in. That's why it just disappears and we're left with the x squared minus 25. So that's what we're factoring. So we say what two numbers add to 0 but multiply to negative 25. Oh. And of course our answer then ends up being negative 5 and 5. All right, so let's take a look at the second one then. X squared plus 49. In this case, in terms of add 2 multiply 2, we'd be adding to 0 again, but multiplying to a positive 49. Well, usually people end up thinking about 7 and 7. But 7 times 7 is 49, but 7 plus 7 is 14. Okay, well what about negative 7 and negative 7? That would add to a negative 14. The only way to add to 0 is to do a positive and a negative version of the same number. So negative 7 and 7. But a negative times a positive is a negative. And in this case, we're having to multiply to a positive. So if you're trying to add to 0 but multiply to a positive, it's impossible. So the second one there, x squared plus 49, is not factorable. All right, then for the third one, x squared minus 1, is that one factorable? Yes. And the hint that we can know whenever we see a setup like this where it's x squared and then a number, it has to meet two criteria for us to be able to factor it. One, it has to be subtraction, because when we saw when it was addition, it just doesn't work. So it has to be subtraction, and then it also has to be subtracting a perfect square. So in this case, yes, it is factorable. Then it's being negative 1 and positive 1. X squared minus 8. Is that one factorable? No. It is subtraction, but the 8 is not a perfect square. And so there isn't a number that we can multiply by itself and get 8. So that one's also not factorable. By the way, if you're thinking, yeah, but couldn't we do root 8? Yes, technically the square root of 8 would work, but generally speaking, we don't want to have to deal with anything that's not a whole number when factoring. And finally, x squared plus 36, is that one factorable? No, because it's addition. If it was subtraction, yeah, but addition, not factorable. Again, remember the reason is because the only way to add to 0 is a positive plus a negative. But a positive times a negative will always give us a negative that we multiply to. So we're going to be using these skills here a little bit later during class. So hold on to these examples and be ready to look back at them. But before we get to those, we also need to practice these. Expanding polynomials by writing them into standard form. So please, for each of these four, go ahead and write each one in the standard form. And so remember how we approach that first one. If we're going to multiply three things together, start by picking two and multiplying those. So I start by multiplying the first two parentheses together, multiply everything in the first by everything in the second. Yes, you could at this point multiply all four of these by both of these, but I do prefer to simplify first. It tends to make my life a little bit easier in the long run, so I simplify it down to be a trinomial times a binomial, then multiply those through. And then here's our final answer for number 1. You get x cubed minus 13x plus 12. Notice that there's no x squared in this line. The whole reason is because when we combine the like terms here, the x squareds end up adding to 0, and so they cancel each other out. It's the only reason why we happen to not have it in this answer. So when doing number 2, we again are going to multiply everything in the first parenthesis by everything in the second parenthesis. When we do that, we get x to the 4th minus 7x squared plus 5x squared minus 35. Now one particular piece of this I want to pull out is why is it x to the 4th? because by making sure you understand why, number 4 gets to be easier. So if I'm going to do x squared times x squared, remember x squared is just x times x. So really I'm doing x times x times x times x. Well, that's just 4 x's that are being multiplied together. That's why it's x to the 4th. Notice the upshot of that is that in order to multiply the x's, I added the exponents, because I had 2 in the first and I had 2 in the second for a grand total of 4. All right, back to our work for number 2 there. We then combine the like terms. Final answer on number 2 should be x to the 4th minus 2x squared minus 35. All right, so on to number 3 now. We approach number 3 just like we did with number 2. Multiply everything in the first by everything in the second. Then combine like terms. You should get x to the 4th minus 11x squared plus 18.
Oh, I can't count.
And then we do the same thing in number 4. And in number 4, we start by doing x to the 5th times x to the 5th. And remember, that means we add the exponents, because x to the 5th is x times itself 5 times, and then that's times another 5 x's. So really it's just 10 x's all multiplied together. So in number 4, we multiply everything in the first by everything in the second, combine like terms to get x to the 10th plus 7x to the 5th plus 12. And then as you take a look at these answers, there's one particular thing I want you to make note of. None of these were quadratics. And yet, all of these last 3 all follow the exact same patterns that we've been observing and using so far this year when dealing with quadratics. You'll notice that the 2 numbers from the original parentheses, they added to give us our middle number, and they multiplied to give us our last number. And since these follow that same pattern, we can use that pattern to factor them. So please start by writing down these 3 problems, and then we're going to work them through together. Now, you basically already know all the techniques for factoring these, but there are certain patterns that tell us when we can use those. So before we actually go into doing the process of factoring these, let's go ahead and take a short little bit of notes. Please add this information into your math notes. So the basic idea behind these notes, the particular part that's most important, is noticing the exponents on the x's here. So what this is really saying is that if you are given a trinomial in which we have 2 x's, and the exponent of the first one is double the exponent of the second one, then we can factor it. And when we factor it, it's going to follow the same rules as when we factored quadratics. So that's really the upshot here. And when we do that factoring, the exponents within the factored form are the same as the exponent that's in the middle of the equation. That is half of the biggest exponent. And so when you go and do that factoring, it is going to work just like quadratics. And so it'll follow the same add to, multiply to kind of rules. Or if we do have a number here for a, even box method would work to factor these whenever we have this kind of a setup. And so if we go back to take a look at these problems now, number 5, the first thing to note is that we have x to the 4th and then x squared. Because the first exponent is double the second exponent, that tells us that we can treat it like we treat a quadratic. We can do the same kind of thing with it. So I'm going to go ahead and start by breaking it up into 2 sets of parentheses. Now, in each of those parentheses, though, it's not going to start with x. Instead, each parenthesis starts with x squared. Remember, that's always going to be either the same as the middle number, or if you prefer to think about it as half of the first exponent, that also works. It means the same thing either way. And so otherwise, it's now the same as a quadratic would have been. We're just going to be saying what adds to 8 and multiplies to 15. And so what are those two numbers that add to 8 and multiply to 15? 3 and 5. So there's our factored form for number 5. X squared plus 3 times x squared plus 5. Of course, make sure you're writing the correct answer down along with the original problems you had written down a little bit ago. Number 6. Same kind of approach. Again, we know we can use our new technique because we have exponents of 6 and 3. The first exponent is double the second exponent. Knowing that, I'm now going to start my two sets of parentheses. What goes first in each parenthesis? It's going to be x to the power of what?
2.
3.
3.
And the reason why we know it's 3 is because this is a 3 here in the middle. Because that exponent is a 3. Or again, if you prefer to think of it as half of the first exponent, of course that's always going to be the same thing. And now I say what adds to negative 2 and multiplies to negative 35. That ends up being a negative 7 and a positive 5. So our factored form here is x cubed minus 7 times x cubed plus 5. And then we go on to number 7. And in number 7, again, I start by noting that my exponents at 4 and 2, the first exponent is double the second exponent, so I can treat it like a quadratic. The only difference is, of course, instead of x plus or minus, it's going to be x squared plus or minus in each parenthesis. And so I say what two numbers add to a negative 14, multiply to a positive 45, and you should get negative 5 and negative 9. But this problem at this point actually provides us with something else. This one, it is correctly factored so far, but it's not actually completely factored. This problem could factor further. Look at each of the two parentheses that we have here. In this case, one of them can factor further. Sometimes both will factor further even, but in this case, one of them factors further. And that's the x squared minus 9. That one's still factorable. And so since that one is factorable, we're going to keep factoring that one. Now the x squared minus 5, that is not factorable any further. So it's going to stay x squared minus 5, but then the x squared minus 9 breaks into two sets of parentheses from there. And so for those two parentheses now that I'm adding in, I'm saying what adds to 0 and multiplies to negative 9. And that ends up being a negative 3 and a positive 3. So that is actually our completely factored form here. Now notice we haven't used any real new skills. We've just seen that we can apply them in a different way. You're still treating everything just like you did when you're doing quadratics. Still using those same add to, multiply to kind of methods. The trick is, though, that as you factor it, check each of these binomials that you end up with and make sure that neither of those can be factored any further. That would even bear going into your notes here. So below the notes that you took earlier, go ahead and add this line. Check if the binomials factor further. To remind yourself that after you factor it, you then need to check and see if it can be factored anything past that. All right, now, we've done some practice problems. I'd now like you to do these two on your own. Factor each of these as far as you can. So let's check in on number 8. So with number 8, notice our exponents are 6 and 3. So since the first exponent is double the second, we can treat it like a quadratic. So in order to factor it, I'm going to say what two numbers add to negative 23 but multiply to negative 50. And I end up getting negative 25 and a positive 2. So it's x cubed minus 25 and x cubed plus 2. And then we have to say, can either of those factor any further? It's tempting to try to factor this first parenthesis further. If it was x squared minus 25, x squared minus 25 can factor further, but x cubed cannot. So there's multiple reasons. One of the reasons is because 25 is not a perfect cube. And if it was a perfect cube, there is a way, but we're not getting into some of the techniques for factoring cubics right now. So if you end up with x cubed, you can know that that one's going to be done as far as it can. So then for number 8, that's your answer. All right, and then for number 9. In number 9, notice our exponents are 4 and then 2. So since the first exponent is double, yes, we can treat it like a quadratic. Just in this case, each parenthesis will start with x squared. And then we say what adds to -5 and multiplies to 4. End up getting -4 and -1. Now we look to see, can that factor any further? Well, x squared minus 4, yeah, that one actually can factor further. What about x squared minus 1? Can that factor? Yes, that can also factor. And the things that tell us that, if you recall from the very first stuff we were doing, is that we can factor them if it's a minus, a perfect square. And since both 4 and 1 are perfect squares, that's what tells us we can do them. And so for number 9, our final answer, we break the x squared minus 4 into x minus 2x plus 2, and we break the x squared minus 1 into x minus 1x plus 1. That then is as far as it can go, as far as it can factor. For one thing, notice, all of these are x's now. None of them are x squareds or anything like that that even could potentially factor any further past that.